visible between -10 and 10 femtoseconds, and which these beatings becomes wider spread when these intensities are increased, which is seen in the case of 210 electron volts transitions, where the beatings not very clearly seen here, but becomes much clearer when the intensities are increased. So in order to understand the dynamics behind this laser dressing, in order to understand how to interpret these processes that are seen on the attosecond time scale, a theoretical model was needed to try to model this laser dressing dynamics in order to support the ideas of the experimental study. So we consider the density matrix approach, where we integrated this density matrix evolution equations beyond the rotating wave approximation in order to account for the high intensities of the infrared pulse, considering a double lambda system, which we consider the electric field as a sum of the electric field of the infrared pulse and also the XUV pulse, considering the delays between these pulses, which is varied between -80 femtoseconds and 80 femtoseconds in steps of 0.2 femtoseconds, and considering the durations of these infrared pulse and the XUV pulse. So the idea here was to calculate the time evolution of the atomic polarization by subtracting the infrared contributions and also using a Gaussian function, window function, centered at 40 femtoseconds in order to calculate and obtain the transmission signals, which we considered for different intensities. So from weaker intensities to higher intensities. In the case of weaker intensities, we observe a strong absorption, which is split between -20 and 20 femtoseconds delay. But in the case where these intensities are increased, we see for higher intensities that this split becomes broader, becomes wider, and starts washing out at even stronger intensities. So the idea is to understand how to compare this theoretical approach with the experimental measurements. And here the idea was to study the dynamics of the transient absorption by applying strong fields. So here strong fields were applied and delay scans were performed for the two transitions. And what was observed here that the strong transmission changes were observed at 0 delays, which was plotted for different photon energies. In the case of 210 electron volts, comparing it with the calculations, and also in the case of 209.3 electron volts as seen by the calculations, which we can see some correlations between the theory and the experiments. Also, in the second transition, in order to see the transmission changes clear, they applied filter to filter the harmonic lines in order to see these transmission changes clear. So they see these transmission changes at 89, 92, and 96 electron volts, which the calculation clearly sees at 91.3 electron volts. So the idea was to compare this XUV transmission for the calculations and also for the experiments, comparing both cases at 91.3 electron volts as seen in the case of the calculations and also the 89.4 electron volts, which we can see some correlations between the experiments and the theory, but with the fast modulation of in the case of the calculation as a result of the temporal resolution of the delay steps. So in order to understand attosecond transient processes and also to differentiate one process from the other and see the contributions of the theory and also of the experiment, the idea here was to take a Fourier transform of the delay-dependent spectrum for the case of the theory, the calculations, and also for the case of the measurement. So what we see here is that the density matrix describes this laser dressing as a very strong nonlinear process, seeing the peaks at 0.75 and at the second and third harmonics at 1.5 petahertz and 2.25 petahertz, which the experiment sees these peaks at the case of 0.75 and also the case of 1.5 petahertz, which in the case of the 2.25 petahertz, they were almost near background noise. But in the case of the experiments, they see extra peaks, which are seen in the cases of 0.3 petahertz and also in the case of 2 petahertz, which are related to the beatings between these two absorption channels, which the theoretical model does not account for. So the idea was to understand the influence of these very high dressing fields by taking a range of the delay. They were taking a range of the delay scan, for particular photon energies, and using a temporal resolution of 170 attoseconds. So the idea here was to study laser dressing for these high dressing intensities, where we see, by comparing measurements and the calculations, a very rich temporal and spectral structures, which is seen in the case of the calculations. In the case of the measurements, these very rich temporal structures is not seen, but the main structural properties can be resolved in both cases of the measurements and the calculations. Where we see some phase shifts attributed to the electric field of the dressing laser pulse, and also plotting the transmission change for the case of the calculations and also for the case of the measurements at particular photon energies. We see some correlations between these, some agreements between these calculations and the measurements. So at lower intensities, the density matrix predicts more prominent absorption changes, which these absorption lines are splitting and becomes wider at higher intensities, but starts washing out when the intensities become stronger, which we can see in this case here. In the case of the calculations, we can see that these absorption lines split into periodic patterns, which these periodic patterns were resolved and also seen in the case of the experiment. So the final part of the study was to study the delay dependence of the XUV transmission at particular photon energies, considering different ranges of intensities, where we can see for the case of 94 electron volts, 209.5 electron volts, and 210.4 electron volts. So what we can see here is that the experimental transmission curves follows the theoretical. The experimental transmission curve follows the theoretical predictions at the case of 94 electron volts and 209.5 electron volts, which we can observe two characteristic peak values, which are more prominent in the case of higher intensities. And also in the case of 210.4 electron volts, we can see some transient gains at lower intensities for delays of -20 femtoseconds. So these gains are also seen in the case of the theory, where we observe gains for the 94 electron volts at +20 femtoseconds for these higher intensities. So this demonstrates how applicable this density matrix model is in seeing the main and most fundamental process in this attosecond time scale by comparing these our simple theoretical model to a more detailed experimental study, and also to see certain processes like laser dressing dynamics and observe how the transmission changes are influenced by the delay scans. So in order to recap on all I've been talking about. So the study was basically about the control of atomic and molecular dynamics interacting with femtosecond and attosecond pulses using the density matrix approach. So in this case, the goal was to achieve coherent control and quantum control spectroscopy by steering populations from an initial state to a target state in one part of the study, which we consider four-level systems representing the energy levels of atomic systems interacting with trichromatic bipoles, considering numerous ranges of parameters, for example, areas, chirp, detuning, and so many others, in order to see how this excitation of these higher states can be influenced. Also, we're able to theoretically achieve successful excitation of the Rydberg state, where we also demonstrated enhancement studies in the case of population transfer and vibrational states, where we consider the rotating wave approximation as a result of the big intensity pulses which were applied in that particular study. And finally, also demonstrating laser dressing processes and comparing it to a more detailed experimental study showing good agreement between the theory and the experiment, and performing this beyond the rotating wave approximation as a result of the intensities associated with the infrared pulse. Thank you very much.
Thank you. Now we are going to ask you some questions. Professor Jordi Montpar.
So I will start with the questions, but first a comment. I like it about the presentation. It was very clear, very nice. But I should say that the written report, at least the first part, it was not so nice. There were some typos, some things that were not very accurate. The figure captions were not not explaining the figures and so on. So that's something that I don't know whether for this thesis, but for your next thesis you should do it. Okay, then some questions. So could you go to the slides from the beginning? let's go on and let's go to the next one. Okay, for instance, one thing that you have said in the presentation